Uh, yeah. So I think we can start. Uh, Welcome all. Welcome to the seventh lecture of this workshop, which is on Introduction to MATLAB, where we learn the fundamentals of MATLAB and then use it for chemical engineering applications, right? So in the last lecture, what we learned was how to find a solution to nonlinear equations in MATLAB uh, through various inbuilt commands that we have in MATLAB. So we looked at the F0, Fsolve, VPA solve, solve, and the root commands, and then we understood the difference between this command also, right? So for most of the part that we will be using non-linear equations in our models, mostly you will find that we will deal with the F0 or Fsolve uh, commands in general. VPA solve and solve generally works with the symbolic equations, but that too we won't be using, at least for the problems that I have considered here. So mainly we will work with the F0 and Fsolve command, where we learned that F0 is a single variable optimization problem solver, while Fsolve is the multivariable optimization problem solver, right? So it uses the multivariable optimization method such as stress region method or the Markov method, while the F0 uses the combination of bisection, secant, or the quadratic interpolation, right? And then we also looked at the bisection method and the Newton-Raphson method, um, how the algorithm of these two method is implemented. So in the last class we coded uh, coded this method through our own code, found the result of this nonlinear equations and compared it with the solution available by this inbuilt MATLAB solvers that we have, right? So that was one thing. Now the in today's class, what we will be doing is we will use this knowledge and then try to solve the chemical engineering problems, which involves the models related to this nonlinear equations, right? So, uh, yeah, before that, I have also shared the class notes. So there were some problems also given. I hope you guys have tried it out. See, these notes are available to you on this Google Drive link, which I have been mentioning all the time, right? So all the notes as well as the codes that we use are available here. And I have also shared the codes for this problem statements that you have. So for this, sorry, yeah. For this 11 nonlinear equation problem, code is already shared, right? So maybe you can check it out. So what I will do, I will just go through one or two problems from this set, so that we recall the idea of the solvers in the MATLAB, and then we will move forward with this problems, four problem which are related to the chemical engineering problems, and then where we will be using the solvers, right? So first, let's consider, yeah, maybe problem number 4, which involves multiple equations, right? So what we have been asked is that we have to find the intercept of a circle, line, and parabola, which is given by this four set of equations, right? So you have a equation of circle, x square plus y square equal to 25. You have equation of line, x plus y is equal to 7. Then you have two equations of parabola, right? And you have to verify whether the solution is correct or not. So let's say use of solver. So first, um, since this are two variables, so it becomes a multivariable optimization problem, right? So therefore, we will use fsolve command because it's a multivariable part. We will use fsolve command to solve this. In fsolve command, what we need is we need the function. We have to provide the function which contains all set of equations, and then we have to provide some initial guess value, right? So let us define function f as two variable x and y, right? Now, see, previously the problem that we had seen in the class, it only included one variable, right? And then one variable, one equation, or even in the multi-variable example also that I had shown, it was just one equation, Can we see it? Yeah, like here. So right now, like we have one equation, but let's say when you have two equations, so instead of just providing function as a single line, you can provide the function in terms of the vector or matrices also, right? So I am creating a vector here where I will provide this four equations that we have to solve, right? So first equation is x square plus y square is equal to 25. So I will write x square plus y square minus 25. This becomes my first equation. Then your second equation is x plus y is equal to 7. So I will write x plus y minus 7. Okay, this becomes my second equation. Why I am writing x plus y minus 7? Because we want to equate this fx is equal to 0, right? So let's say this is your equation fx, which is x plus y equal to 7. So when you want to solve it, the value of x and y, which will which will satisfy this equation. So what you create is a function that will be x plus y minus 7 is equal to 0, and you solve for this x and y, which provides the value such that your entire function becomes 0. So that's why you provide a minus sign. Okay, then the two parabola equation is x square is equal to 25 and x square is equal to 16. Okay, so x square minus 25 and x square minus 16, right? So these are my four equations. I have provided into the column format. You can also provide them into the row format, or anything is fine, right? So this is my function. I have defined it. Now solution to, so my answer will be, which is solution to this line, or let me call it as an intercept. Intercept is equal to my f solve. Why I've solved? Because it's a multivariable optimization problem and I have to provide some initial guess, right? You can see in the help command it shows that you have to provide the function and the x0 value. And if you further want to see how your method has converged or different options, then you can provide the option part, right? So let me provide the guess value as 1 and 2 and see how it works. Okay. So this is my part and then I will run it. Oh, it's failing. Why it is failing? Because incorrect dimension for raising a matrix to a power. Okay. Yeah. So here we have provided the function in terms of x and y. Right now, this function doesn't know x and y, what are its values are. Okay. So instead of directly using the power raised to the power 2, we have to use the dot product of that function. Sorry, dot power. If you recall the earlier classes, we had mentioned that for the summation and the multiplication of your vector, you have to use this. Still, we are getting some error by 25 x square minus 16. Uh, so this is x square minus 25, x square minus 16, x and y. The methods are correct. Maybe I'm providing it incorrect. No, this is not the correct syntax. Just give me a minute. What happened? So here, let's solve various solvers. This is problem number 5. No, 4. Yeah. I'm providing x0. Oh yeah, sorry, I realized my mistake. So here we are putting function x0, y0. X comma y. So what if I write it this way? Again, I'm getting some error, just not enough input argument. So let me remove this dot product part. Fail in initializing option function value F solve. Okay. We are getting some error which shouldn't come here. This is F solve. Just give me a minute. So maybe here it should be X solve, F solve, intercept is equal to F solve. Let me write it this way, at the rate, and this part X comma 2, and then when I run it, failure initializing object function F solve cannot equate X comma Y, and missing argument 1 comma 2. We are getting the answer. Function is defined correctly. So if I just directly place it, it should have given me the results. Oh, sorry, I realized it. So it should be the xSolve function f x0. So here the function is defined correctly, but variables are not. So maybe the intercept is equal to this. Incorrect dimension for raising up matrix power. Check that matrix is square and power is scalar on the each element, which doesn't make sense. 1 comma 2. I don't know why I'm getting this error, but essentially it should work. So here I have used, instead of x and y two variable, I have used x as a vector, and then I'm supplying its value as x1 and x2, and it was giving me the correct result. But right now we are getting some error, which should have been easily solved. Let me do help f solve. Let's look at some of the documentation example. Maybe that might help us. Is anyone joining yet? No. That's okay. So param x and y, x1, x2, cx1, x2. This is also fine. So this is x1, x2, c, x solve, x0 options. Um, okay. So let me check why the syntax is exactly not working. But let's say instead of this, if I do Control C, let me comment this part. And let me use the previous method which I had used, was that if I write x1, x2, okay, here also x2 and x1, x1, x2, and then when I call the function, yeah, so this time it's solving it and it's giving me the value of x1 and x2 as 3 and 4, right? Uh, so you can see this 3 and 4 value will satisfy all the equations. But why when I'm providing it in terms of x and y, it's not giving? I have to just check. So what I will do, I will verify what exact syntax error I have, and then maybe come back to you guys with the exact error. Right now, I'm not able to recall or why this exact error is coming. Right? Maybe in next class I will begin with this part. Okay. So this is one example where you have multi equations and then you can solve. You can find its solution with the help of fsolve. Similarly, let's say here you have example, and so you want to find the symbolic solution of the given equation. So you have three symbols x, y, and z, right? Now you don't know, so your solution will depend upon what is the value of c. So you don't know the value of c. So in such cases, your answer will come in terms of the coefficient c, right? So this becomes in symbolic equations or symbolic solutions, right? So that's why what you have to do is you have to define two symbols. So I will define sims x, y, and c part. Okay. So these are my three symbols. Yeah, sorry, x, y, and c. And then my equation f becomes so x square plus y minus c, comma x plus y square minus c, comma c minus 4. Now to find a symbolic solution, which function we will use? So see, what options we have in the solvers. So you have fsolve and f0, which are for the numeric solution, vpa solve and solve. Vpa solve finds the numerical solution of the symbolic equation, while solve finds the symbolic solution to a given equation, right? So that is your solve part. So then I can use solution is equal to solve bracket f, which I am providing, and then your variable x comma y comma c, and then if I run it, it has thrown me some errors, minus c, some errors. My function, so my function is this, and then if I run it, let me separate them column wise and see. Mhm. Oh yeah, sorry. Oh, again, my this is my mistake. So basically, when we are solving it, so when we are using the symbols, we have to instead of writing function is equal to 0, we have to write the equations, right? So this is my equation. So it should be equal c. So x square plus y is equal to c, and then x plus y square is equal to c. That will be the my solution. C is equal 4, right? And then you can use solve and then your coefficient x, y, and c. And then if I run it, let me, remove this part. So this is your solution. So your sorry, these are your equation, and then your solver list of equation must not be empty. Get equations. So here, I think people are starting to join. Yeah. Okay. So you have three equations that we provided: x square plus y is equal to c, x plus y square is equal to c, and I'm using solver. Uh, just give me a minute. Yeah. Hello. Yeah. So those of you who have just joined, so what we were discussing was the solution to this non-linear set of equations through the MATLAB, right? And if you have seen the last class lecture, the video for the last class, the inbuilt MATLAB solvers that we have are the F0, Fsolve, VPA solve, and solve command, right? So where F0 and Fsolve are the numerical solvers for single variable and the multivariable part. VPA solve and solve works with the symbolic equations, where VPA solve gives you the result for the numerical value, while solve gives you the exact solution, right? And we, as I was discussing that in the previous class, what we had done was we had looked at the various example of the solvers, right? Then we try to understood some basic methods such as bisection method and the Newton-Raphson method. We coded it out, and uh, then compared our result with the uh, solvers that are already available in MATLAB. And then right now we are looking at some of the examples of that problem, right? So first example that we looked is this part, that you have to find the intercept of given equations, right? So you have four equations given: circle, line, and two parabola. And if you want to find the solution of that, right? So what we do, we first define that function. Okay, so I'm defining function in terms of vector x. So that x1 and x2 will represent my x and y variable, right? And I'm writing out this equation, and you use fsolver to call this command to solve this function, right? And you provide some initial guess, and it gives you the result, right? So when I'm running it, I'm getting a solution intercept as 3 and 4, right? And then, so the second part is to finding the solution to the symbolic equations, right? So here you have symbolic equation. This is the problem statement, that find a symbolic solution to the following equation: x square plus y is equal to c, x plus y square is equal to c. So here c is equal to 4 is given, but let's say in case you don't know the value of constant c, then how you will find the solution, right? So in that cases, your solution will become dependent on c. So that's why we have to solve it symbolically, right? So that's why we are defining symbols x, y, z, x, y, and c, writing our equations in terms of x, y, and z, and then calling this solver part. Okay, so if you do that, and if I run it, okay, so if you run it, so you will get your solution in terms of this solve part. And when I look at what's inside the solve, right, so it's variable x and y. Here, yeah, solve structure. Right. So it gives you the x and y value in terms of the coefficient c, right? So once you know the value of c, you can substitute it and then put it in form of the equation, right? I can also display the solve part. No, not this way. Display solve 1 comma 1. What was the better way to, sorry, display solve dot x. Yeah. So since it has two component and it's a symbolic solution, so rather than I will write solve dot x, right? So this is your equation of x and y in terms of the coefficient c, right? So you could have either this solution. If your x is this, your y will be this. If your x is following this equation, your y will follow this equation. So same way you can get the symbolic solution also. So you can put the value of different constant c and then get the answer, right? Now, with this idea in mind, and the with the idea of how different solver works, Let's look at the some of the chemical engineering problems that we want to where we want to utilize the solver to find the specific solution, right? So first example is flow through pipe which has a multiple sections. Okay, so what is the problem statement? That you have a piping system which contains three different section which are transporting water at 20 degrees centigrade. Water density and viscosities are given. The system is laid horizontally, the flow is steady and incompressible, and the three different section pipe informations are given. What are their length, diameter, roughness, as well as the flow rate, right? So what we have to do is calculate the head loss across the entire pipe using the Darcy-Weisbach equation and the Moorjani chart or the Colebrook-White equation to find the fanning friction factor, right? We have to assume that the flow is turbulent and you have to use the MATLAB solver to implicitly solve the Colebrook equation, right? So let's first recall what is this Darcy-Weisbach equation and what is Colebrook equation. So if you will recall your fluid flow phenomena, so flow when fluid is flowing through the pipe, you are bound to get some sort of a head loss due to the frictions present inside the pipe, right? So due to the friction between the fluid and the pipe wall, you will get some friction. And this Darcy-Weisbach equation correlates the pressure loss or the head loss inside the pipe with the velocity and the friction factor, right? So this is your Darcy-Weisbach formula. So it gives you head loss as a function of friction factor into the velocity and the dimensions of your pipe, right? So this is my Darcy-Weisbach equation. This is the modified version. So essentially both are same, it's just translated. So here it's in terms of the head, here it's in terms of the pressure top. So if you divide this side by pressure, so delta P by rho G will give you the head value. So that is friction factor into V square by 2G into L by DH. Okay. So this is your Darcy-Weisbach equation. So when a fluid is flowing through pipe and I want to find how much head loss will have, so that what information I need to know what is the length of pipe, you need to know the L, you need to know the D, which is the diameter of pipe, you have to know the velocity, you have to know the rho, which is the density, right? Okay, this information is needed, and another is the F. Now F is the friction factor which we have to find for the pipe. Now if you will go further into that, so there is something which is referred as the Moody diagram or Moody chart, right? So this is something you might have seen in your fluid flow classes. Okay, so in Moody chart what we get is we get the relation between the planning friction factor and the Reynolds number, right? So now your fluid flow is divided into two regions, one is the laminar and one is the turbulent. For laminar region your friction factor and the Reynolds number follows the straight line relation where planning friction factor is 64 times Re, while for a turbulent region, depending upon what kind of roughness you have, roughness, this is the relative roughness. So I mean roughness which is the which shows the internal characteristic of your pipe, right? What kind of pipe you have, depending upon your pipe material, you see you have different roughness values available. So what kind of roughness you have, you will follow this friction factor versus Reynolds number graph, right? Now, ideally, when you are computing it, what you would like to do to understand what is the friction factor inside this pipe is that you will first find the Reynolds number, and corresponding to that Reynolds number, what friction factor you have. You find that friction factor and you put into your Darcy-Weisbach equation, right? Here to find the total head loss that is occurring in your system. But every time it's not possible to look into this Moody diagram, right? Specifically when you are using programming language, you cannot utilize this information. So rather better thing would be if you have some sort of a numerical expression with, or the empirical expression which represents your Moody chart. So that's where your Colebrook-White equation comes. Okay, so this Colebrook-White equation, what it does is, yeah, this is your Colebrook equation. It relates your fanning friction factor with for the turbulent flow with the Reynolds number and the roughness factor. So for any fluid which will follow in this turbulent region, it will follow the Colebrook equation, where the relation between the Franning friction factor and your Reynolds number as well as the roughness factor is given, right? So if I want to find, let's say for some flow condition, I know the Reynolds number. If I can use solve this non-linear equation, so right now you can see this is actually a non-linear equation. Why it's non-linear? Because you have this logarithmic term, your friction factor to the power half, right? In both cases, so this becomes a non-linear implicit equation, right? Because you have to solve the equation such that both sides become equal. So basically, you are minimizing the fx, you are optimizing the problem where fx equal to 0 occurs, right? LHS minus RHS becomes 0. So for a given Reynolds number, you select the different values of FD, and one which satisfies will be your the Franning friction factor. Okay. So what we will do is, what problem we have given. We have been given that the we have the pipe dimension. So water is flowing through three different pipes, and these are the information. Now I have to find the pressure drop inside this pipe. So I have to use Darcy-Weisbach equation, where I need the friction factor. To find the friction factor, you have to rely on the Colebrook equation, which is difficult to solve by hand, right? So we will use the numerical method to solve it, and specifically rely on the MATLAB command, which is the fsolve command, to find this solution. Okay, so that's the idea. And once you have found the friction factor, you can put it into the original Darcy-Weisbach equation, right? So this is the flow through pipe problem. What information you have? So the information that we have is, we know the temperature, we know the density and viscosity of the fluid. Okay, so density, I'm calling it as dense, that is 998. I'm commenting the units here so that I know what kind of unit I'm working with. Viscosity, so I'm writing viscosity. I'm writing viscosity. Yeah, viscosity is 1.002, and its unit is given as Pascal into second. Sorry, 1.002 into e to the power minus 3. Yeah, this is how it's given. Okay. Then you have three pipe and their information is given. See, flow rate is the same. So my flow rate is constant. So flow rate Q is equal to 25. Okay. Now this is in liter per second. Okay. So if I have to convert it into the meter cube, I will multiply with the 10 to the power minus 3, right? So this becomes meter cube. I am converting into the SI units, right? So this is my flow rate. Now what we have is, we have this pipe information. So I will create a matrix which contains the pipe information, right? Where row will correspond to pipe number data, and the column will correspond to the specific property that we are looking at. Okay. So I'm creating a matrix which is referred as pipe data, where first row is for pipe 1. So values are 100, 150 and 0.1. 150, 0.1. Second row 75, 100.2, 75, 100, 0.2. And the third row is 50, 200, 0.05. 50, 200, 0.025. Sorry, 0.05. Right? So here, this is pipe 1, right? Then this is pipe 2, and lastly you have pipe 3, correct? These are the information, and your column will correspond to length, then diameter, and roughness. So roughness, I'm calling it as E. Okay. You can just put it nicely in this way. Right? So now it makes sense. This is the pipe information data or the pipe data that we have. So this is one information. Then, uh, okay. So now rest of the thing we have to calculate it, right? So what I will do, I will create first. We have to find the head loss, right? So I will create a variable which says total head loss. Okay, it starts with the value of 0. We will set up one for loop. That for loop will go for all three pipes, right? So for loop, I will start one variable which will start with 1 and go to the length of pipe data, right? That too, it's a matrix, right? So if I just write, and if I write the length of pipe data, I will get the answer, the maximum length. Okay. If you want to be so thorough, then maybe you can write. So you want to know you want to take out the how many rows you have, right? So either you can use the size command. So size command gives you the pipe data. It gives you the row comma column, right? So if I write size comma 1, it will give me the row information only. So either you can use size or you can say the length of pipe data, but consider only the first column. Okay. So when I do that, function interesting, what happened? Pipe data, all row comma 1. Sorry. Yeah. So when I can call this, so there was a syntax error, right? And then I can find the length of this. So there are various ways. You prefer any of the way, right? So there is no one specific correct approach. You decide what kind of approach you want to use. So this is my for loop. This loop runs for number of pipes. Okay. Then once I'm let's say I'm considering the first pipe information, right? So first thing that you have to do is find the Reynolds number and so no, first thing we will do is we will take out the information for that pipe, right? So right now I have L, D and E stored in the pipe data. So I will write length, or just I can write L is equal to pipe data. So this is your first row, first column gives me the length, right? Diameter is given by pipe data, first row and the second column. So second column gives me the diameter. Now here one thing, this diameters are in mm and roughness is also in right? So it's better to put a notation so that you know your data is in which unit. Okay. So what I will do, I will convert them into convert them into meter from right? So here diameter will become D by 1000. Okay. Similarly, E value becomes pipe data, your third column, it provides you the E value, right? So now you have length, diameter and E. Okay. So first, in order to solve the Colebrook equation, right, you need the information of Reynolds number, and your Reynolds number is given as rho VD by mu, right? So first I will find the Reynolds number Re, which is density. I'm writing dense rho velocity. Now, so velocity we will need. So that is velocity into viscosity, sorry, not viscosity, diameter divided by mu, which is your viscosity. So this is your Reynolds number, but we don't have velocity as of now, right? So what I will do, I will find the velocity since we know the flow rate Q, right? We know the flow rate Q divided by your pi into d square by 4, right? So this information, your flow rate divided by the area, this will give me the velocity. Okay, this velocity I'm using here to find the Reynolds number. Now I have computed the Reynolds number, right? Now what we have to do, we have to define a function which represents our Kolbe equation. Okay, so for that, let me just copy paste it because I think we are running late. Uh, So see here I'm slightly doing it I'm doing it in much nicer format. Okay, I have written it in much nicer format. Your Reynolds number rho Vd by mu. Yeah, this is your Kolbe equation. Let me make it bigger. Yeah. So I'm defining the Kolbe equation for the friction factor, where function is written as Kolbe, which is at the rate f, variable is my Franning friction factor f, right? Now how my equation should look like? So it should be the fx is equal to 0, right? So here first term is 1 upon under root fd, right? So 1 upon sqrt fd, which is my Franning friction factor. Then this term will come on the left hand side, so it will become plus 2 times log 10 of this term. Okay, so if you will see, plus 2 log to the power 10, log base 10 into epsilon. Instead of epsilon right now I'm using the variable e, diameter e by d divided by 3.5 plus 2.5 times Reynolds number into sqrt of f. So this is your Kolbe equation which you have to solve. Okay, so my friction factor f will become f solve. I am writing the my equation Kolbe, provide some initial gas. So I'm providing some initial gas value of 0.01. Okay, so right now I don't know, that's why I'm providing this value. Once you know the value of your friction factor, you can use your Darcy-Weisbach equation, right, to find out what will be the pressure drop. Okay, so right now let's say I'm using this part to find the pressure drop into the head. Okay, so I'm using finding f value which satisfies the above equation. This we have done it. Now finding the head loss. So your head loss H will become, what's my equation? My equation is friction factor into V square by 2G into L by D. So my F into V square, which is your velocity. So velocity square divided by 2 into your G, which is 9.81, right? This into your L by D term. So which is your length divided by the diameter, right? So this is head loss in one pipe. I will add this head loss to the total head loss. Total head loss equals total head loss plus your H. Okay. And once this loop ends, you will have crossed all three pipe information, updated their data, and computed the head loss through them. Okay. And at the end, I will print f the total head loss through three pipes is, okay, you can write it as percent F, this is in meter, okay, slash n, comma, total head loss, right? So this is how we have coded it. Now let's run and see whether it's working or not. Okay, I'm getting some error here, line 4. Oh, I don't have to write in multiplication sign because it will directly take it. Clear all, CLC. You can comment this part also. Sorry, not comment, suppress the output. And let's run it. Right. So this is how you are getting total head loss through these three pipes is 10.766 meter. Okay. If you want to convert it into the pressure value, you have to multiply it with rho and g. Okay. The density of water and the your gravitational constant. Okay. So this is how you can compute the friction flow of frictional loss in a pipe. Okay. So this was the problem one. So here what we did was we first translated our problem into the mathematical model, right? So we identified what mathematical category it falls. So we knew that we have to use the Darcy-Weisbach equation. Then the information that we need is the Franning friction factor, and to solve that we have to rely on the Colebrook equation. And this is not an easy solution, so it's a iterative calculation, right? So that's why we relied on the MATLAB inbuilt solver fsolve, which solves the non-linear equation. We found out its value. Okay, so we found the category also that this is a non-linear programming. So first modeling the system, identifying the numerical method. Once you have done that, the next step is to code it out, right? So we put the information, we compute the required values, employ the numerical method to solve that particular set of equations and find out the solution, right? So this is how the approach works. Now let's look at the second example, which is laminar versus turbulent flow in the pipe. Here we have to compare the head loss for laminar and the turbulent flow in a smooth pipe, right? So here the one information is given is the smooth pipe. We have been given the diameter, length, water properties, and two velocities are given. Now, in this Moodye chart, so this friction factor values, so this Colebrook equation is holds true for the turbulent flow, right? But when we are in the laminar region, right, there the friction factor value will follow this equation 64 by Reynolds number, right? And as you see here also, this is how it follows. Okay, so if we are in the laminar region, we don't have to employ the Colebrook equation. We can just directly use this equation. Or and if we are in the turbulent region, then we have to use this equation. So we have these two conditions that we have to put it in, right? So we will code it accordingly. I will write laminar versus turbulent flow. What information we have? We know the pipe diameter length. Length is 100 meters. Okay, it's in meter. Diameter is given as 50 mm. Okay, so it will be 50 divided by 10 to the power 3. Okay, this much meter. This is your length, diameter. Then you have water property also given. So density is 998. This much kg per meter cube. Then you have viscosity again 0.001 Pascal second. Viscosity 0.001. This much Pascal into second. I'm suppressing the output, so I don't need to see this value again. Okay. Let me say this. Okay. What other information you have? You have two velocity value, 0.1 and 3 meter per second, right? So I'm writing velocity is equal to 0.1 comma 2 this much meter per second. Always a good practice to start with clearing all the variables, right? So now we know that. So first thing here, we will have to run a loop which will go through both the velocity. So for I will start with one for loop which goes to the length of vector velocity, right? I will take out the velocity v as vel comma I, sorry. Okay. So this is my velocity. I will find the Reynolds number which is rho into velocity into diameter divided by viscosity. Okay. Now, based on the Reynolds number value, we have to decide whether we are in the laminar region or the turbulent region, right? So I will use the cutoff of Reynolds number here. Though we use generally cutoff of 2100, I am right now considering this as a reference. And there they are saying that around 3000 we will consider as in a laminar part, rest we will consider in the turbulent part. But if you recall your fluid flow phenomena, we go around 2100 till that point we consider laminar flow. Greater than 3000, 4000 onwards we consider the turbulent, and in between you have a transient region. But right now we are not worrying about that. So I will do what I will do. I will consider if the Reynolds number is less than 3000, then we will consider the laminar flow and use this equation, right? So we will put the condition if Reynolds number is less than 3000. I will write the flow is laminar. Then my F becomes, what's the value? 64 by Reynolds number, right? This is the value. So it becomes 64 by RE. Then my head loss, H, that will be nothing but this part. Let me just copy paste it. So it's your head loss is friction factor F into V square by 2G into L by D. Correct? If Reynolds number is greater than that, that means we are in the turbulent region. So I will print that the flow is turbulent. I can put slash n so it starts with a new line. In that case, you have to again solve the Kolyuk equation, right? So I will just copy paste this part. Just I am using the different notation, nothing else. Right? Here. And in that case, F is computed from solving the Colebrook-White equation. This ends the if condition, and further the for loop is also added, right? Now here you can put, once the if condition is added, you can print the result as the head loss for given velocity percentage F is percent F. Then you have your velocity value V, your head H. Okay. Right. See here I'm not updating the H because it will be computed every time for the pipe flow and I'm printing it. Right. So this will be my strategy, and let's run it and see whether it's we have coded it correctly or not. Okay, we got some error. That is failure in the initialing object evaluation. F solve cannot continue. Oh yeah. one more thing. Okay. So I just copy pasted the previous equation where we had the E by D part, right? So here, what has been given to us in the problem is that the flow is in a smooth pipe. So for a smooth pipe, you won't have any roughness value, right? So if you have a smooth pipe, then your roughness factor goes to the 1. Okay, for a smooth pipe, mm, not 1, sorry, point 0, sorry, it goes to the 0. For a smoother pipe, it will go to the 0. So then you won't have this E by D term. Okay, so this term will vanish, and then you will end up with the this portion only, 2.5 times Reynolds number by FT. Correct? Yeah, if I'm not making any mistake, this is correct. Rough region, yeah, smooth pipe is this. Either you can use some other equation also, but I'm just putting the uh, friction factor value as, sorry, the roughness factor as 0, right? So that means we have to get rid of this part, and once you do that, and then this, F into velocity. Yeah. So this is what happens when you directly copy paste it, and there are same variables. So our velocity is defined by capital V. So I have to write V square by 2G L by T. Okay. So we have got two results. The head loss for a given velocity is this. The flow is turbulent. The flow is, right. We are getting the flow is turbulent. Again, the flow is turbulent, and these are the head loss that we get. So for first case, since the velocity is low, we are getting the 0.0381 as a head loss. For the second case, for the given velocity of 2, your head loss is 7.33 meter. Okay. Obviously, you can write it in a much nicer format than this. I have just shown you here the reference code which are outside the in-class folder. There you will see that I have wrote them very nicely and neatly. Okay, you can check that also. Right? So this is how it works, and you get the result. Okay, so this was one. Now, so what I will do, we will go through two more problems. Right? So problem 3 is fairly small, and then problem number 4, and then after that we are done. I think it will take 10-15 minutes. Then you guys will be free. Okay. So problem 3, here the information is given that you have adiabatic flame temperature T. For the adiabatic flame temperature for burning methanol with 100% excess air in the furnace is given by this equation. Right? The adiabatic flame temperature is the upper bound of temperature that is reached by the actual process and serves as an important parameter during the furnace design. So we have to find this flame temperature correct to two figures after the decimals. Okay. So we have been given this equation. Now, if you will know, this is the polynomial equation, right? And you have to solve this equation. So what kind of solver will we use? So if you recall, in the last class, we also looked at the root command. Root command specifically is used to find the solution to the polynomials, right? So this is how it works, that you have some polynomial. Uh, sorry, root or root command. Yeah. So there is s in that. So if you have some polynomial which looks like this, where you have coefficient to the x to the power n up to n plus 1 coefficient, and then you can call this root command in this manner. This way. So for the equation something like this, your coefficient will become 3.13 minus 2.21 and the constant 5.99. You can call the root command, provide this vector, and it will give you the results. Okay, so it will solve the function which satisfies the this polynomial. You have to just provide the coefficient of that polynomial, and it will give you the answer. Right. So this is also one polynomial. right? Let me copy paste and finding the adiabatic temperature of furnace given by polynomial. So this is how your polynomial looks like. Okay. This is t square, t cube, t square into t. So I will write one coefficient vector which is 1.3 e to the power minus 8, comma 4.9 e to the power minus 5, comma 0.47, comma constant value 681.7. So all the coefficients are listed down. Let's say you have some in between missing value. So let's say this was t to the power 4, then you get directly t to the power 2 and t. So that means t to the power 3 is 0. So you have to add 0 part also. Okay. Right now we have a polynomial of the power 3. That means I will have 4 coefficients, right? And these coefficients are written in the order. First will be the highest power, then -1, -1, and the last will be the constant value. So this order you have to follow. And then I can write temperature is equal to, I will call the roots command. I will provide the uh, polynomial coefficient matrix C, right? And see what answer you get. This is furnace example, right? So this is your answer. So this comes to be, now right now you can see there are 3 values I am getting, and let me write it much nicer way. Display temp. Okay. Clear all CLC and it. So these are the values. Now here you see there are 2 values which contains the imaginary part, right? Since it's a cubical equation, you will get the 3 solution. Out of the 3 solution, one is the real solution and rest 2 are the imaginary solution. Why this is real solution? Because the imaginary part has a 0 multiplication, right? Okay, so that means only the real part will be considered, which is 1.2381 into 10 to the power 3. So that means your adiabatic temperature will be uh, sorry, 1238.1 Kelvin, right? So this is how you can use the roots command. Now same thing you can also, like same problem you can solve with the f0 or fsol command also, right? But there what you have to do, you have to write them this temperature equation in the some functional form of temperature and then provide it into the fsol command, right? Rather than that, this strategy becomes much easier. We can do that also. Let's say my temperature is fsol, right? I'm writing the function of iterate t. Some initial guess you have to provide. So let's say I'm providing the value of 500, and here I have to write the entire function. So let me do this into t into t squared into t cube. So this is how your equation looks like, right? Correct? So t cube, t square, t, and that's one. And then some initial value. And if you do that and you display the answer, so this is your result. Now here the fsol is providing the real result only because it's an optimization problem and it works based on the initial guess. So initial guess is 500. So based on that value, it will use the optimization method whichever it prefers, which best fits your which best fits your equation, and then find out the solution. So that's why here you are getting only one solution, while in the roots command you are also getting the imaginary solution. So with both of them, you are getting the actual solution, right? But then you have to decide which which solver will best suit for your equation or suit for your problem, right? So let's say if you are using the roots command, so you will get inevitably will get the three solution, and out of that three solution you have to find out which solution will be useful, right? So obviously this imaginary part doesn't make sense for the real world scenario. You have to select the real part. So then you have to put some category when you are using the roots command that my solution should be real. While in the fsolve command, you are directly getting the results, right? So again, every method has some advantage, disadvantage, but which method to use will depend upon what kind of problem you are solving. Okay. And then lastly, the final problem is the steady state CSTR problem. Okay. Uh, so in this problem, what have been given to us is that a CSTR is used to carry out liquid phase irreversible reaction A giving the product B, and the reaction rate is of the second order, which is given as KCA square. We have been provided with the reactor data. So you have the flow rate data, initial concentration, rate constant, and the reactor volume information available, right? We have to find the steady state conversion X, which satisfies the CSTR design equation, right? So this is our problem statement. So first thing will be to model our system, right? So how we will model the system? So if we will follow the mass balance around the CSTR, which is flow in minus flow out plus generation minus consumption is equal to accumulation, right? Now, since it's a steady state CSTR, right? So we have been asked to find the steady state conversion. So accumulation will become zero, right? So if you will recall your reaction engineering classes, okay? So this is how we derive it, right? So at the end, you will end up with this sort of equation, okay? So that in minus out plus there is no generation if I write it in terms of the x minus accumulation, sorry, minus disappearance. So you will get this sort of equation which will represent the steady state CSTR, right? Here your rate is given as k Ca square, out of which Ca you can also write in terms of the conversion, right? So this is your equation. V is equal to Fa0x divided by k Ca0 1 minus x square. Now, what have been asked to us? Like we have the information of the initial data, we have the rate data, we have the volume of the reactor, and we have to find the conversion x. So if I just look at this equation, what comes to my mind that this is a non-linear equation, right? Because I have conversion in the numerator as well as denominator, and then I have the power to the conversion, right? So it's a non-linear equation, and to solve it, obviously I have to use the some iterative process because I cannot directly guess some x value which will fit this part, right? So I have to rely on the some numerical method which will give me this function as the which will give me LHS equal to RHS. So if I have to find it, convert it into the optimization problem, my function will become function of conversion x, which will be v minus this RHS term is equal to 0, right? So I have to find the value of x, which will give me v minus this right hand side term is equal to 0, right? So this we have identified, we have modeled our system, we have identified it's a non-linear programming problem, right? So then we also know, we are currently doing that only, that we know how to solve this non-linear equations, right? So steady state CSTR problem, you will write it this way. What has been given to you? Let's take out all the information that has been given. Volume as 2, this much meter cube, Fa0, which is the molar flow rate 2.5 mole per second. Then you have concentration Ca0, 1.2 mole per meter cube. Now, remember, whenever you are using programming to solve any problem, just be thorough that your units are correct. or and they are consistent, right? So K is equal to 0.7 meter cube per mole second. And 5 meter cube per mole second. This is similar to whatever calculation you do by hand, right? Because if there is some issue in the unit conversion, then your result will vary drastically. Okay. Now I have to define the CSTR equation which follows this part. Right? So I will create one function which says steady state CSTR is equal to, it's a function of my conversion x is equal to v minus this entire term which is fa0 into x divided by k into ca0 into 1 minus x square, this entire square, ca0 into x square. You can put another bracket. One more thing to be careful when you are working with a longer equation is that you know where the correct power begins and ends, where the multiplication starts or ends, right? So instead of, so here CA0 into 1 minus x to the power 2 should come, right? So instead of this, if I put the power by mistake here, then this will become, I'm only considering 1 minus x to the power 2, not the CA, right? So be careful when you are using the equation which has a longer format. So one thing could be you can break it into the smaller parts and then write it down, or or just while writing be very cautious with the spaces, etc. Right? So that way you understand where your equation starts, your equation ends. Okay, so this is one thing. So this is my CSTR function. Now I have to find the conversion at steady state is equal to fsolve. I can call my function steady state CSTR. Some initial value we have to provide. I don't know the value, so right now I'm providing the value of 0.5, and let's run it and see what kind of solution we get. Right? So we are getting the steady state conversion as 0.2902, right? So that what has been asked to us, that we have been provided the CSTR data and we had to find the conversion at a steady state based on this data. Right? So that's what we did. Now here, so this is just a simple part. If you want, you can do sensitivity analysis, etc. also, right? So here the fixed volume is given. So let's say instead of the fixed volume, you want to understand how the volume of reactor will affect my conversion, right? So instead of 2 meter cube volume, let's say what happens, I have 2.5 meter cube volume. What happens, I have 3 meter cube volume, right? So you want to see the trend change in the conversion with respect to volume. You can model that part also, which is fairly simple. So let's say uh, create just small simple for loop which says volume V changes from 1 to, let's say I change it to 25 at an interval of point 0.5. Okay. In that case, my V becomes, so this is my volume. So in that case, my conversion, okay, so let me update this V is equal to volume. So I'm updating the volume value based on my function, and I can just call this part again. Conversion at steady state is this. Okay. So this will give me the conversion at every volume value. Now you have to store that conversion also. So let me say x with v. I will create one vector. Okay, I'm just creating one variable x with v, and Oh, sorry. I have to create one vector with a proper length. Right now, let's not go into the different variable length. So rather, I'm creating one volume vector and I'm creating one vector which is zeros and that has a size of wall vector. Right. So for each wall vector, I'm first creating the conversion 0, right? And then what I will do in this for loop, once I'm computing it, I will update that value as conversion at steady state. Just let me make some changes. I is equal to 1 to the length of wall and this becomes I. Correct? So what I'm doing, I'm running one loop which goes to the length of volume vector. It will take that volume, put it into the conversion equation, find the conversion, and then at the end, I can just directly plot volume versus x with v, okay, and see how it works. So you can see it's actually not changing much. Wow. It's almost remaining constant. X with volume conversion. V is updated every time. Yeah. FA0 is same, CA0 is 7.5. This is very strange. It should update. So let's say instead of 2, I start with 1. I start with 1 and 5. Okay, maybe right now the data is said that the conversion is not changing much, but you should be able to get the change in your reactor conversion depending upon the change in your volume. Like this is very strange to me. It should have happened. I think the steady state part has not changed. V is changing. So conversion, first the steady state conversion was 0.029. So if I write this as 0.2902, I'm getting no error. If I want a conversion of 0.3, 0.4, 0.5. Apparently for each value we are getting the same answer, which is slightly weird, but maybe it could be some. So these are the arbitrary data, right? So that's why it's not. Maybe probably it's not varying too much. But let's say if you have an actual data, then you will get a correct trend. How the change in the volume is affecting a conversion. Let me go through this data once more. I will check whether I have made mistake or maybe it's just the initial condition that we have selected. Okay, so I will update you in this result as well as something that we were looking at the start solver example where this app solver was not working with variable x and y. So this two information I will give you, update you what exactly error was that in the next class. And then from next class onwards, we will work with the problem which involves ordinary differential equations in our system and how to find the solution. Right. So that's it from my end today. Thank you for joining.